In 4.3, we're going to look at modeling quadratic functions. We'll learn how to model data with a quadratic function, meaning how can we take information that we have and see if it fits in a quadratic model, and how can we interpret real-world quadratic scenarios. A quadratic model is an equation in the form of y equals ax squared plus bx plus c that copies how things work in real life. We could also have the equation be in vertex form, but more often we're going to see it in standard form, hence the name standard form. Campers at an aerospace camp launch rockets on the last day of camp. The path of rocket 1 is modeled by the equation h equals negative 16t squared plus 150t plus 1, where t is the time in seconds and h is the distance from the ground. In other words, how high the rocket's going. The path of rocket 2 is modeled by the graph at the right. Let's label this. Our equation here is rocket number 1, and our graph is rocket number 2. First thing we want to know is which rocket flew higher. This means we need to know where is the maximum on both of these functions, or the parabola. The maximum is always going to occur at the vertex. We'll find the vertex the same way we did in 4.2. First, we need to know our a value, which is negative 16, and our b value, 150. Normally we would say x equals, but since we're using t in place of that variable, we're going to say that t is equal to negative b over 2a. So we'll have negative times 150 divided by 2 times negative 16. And this comes out to be 4.69. But this is only the x-coordinate of our vertex. We need to find the y-coordinate, or our height. So our height will be equal to negative 16 times 4.69 squared plus 150 times 4.69 plus 1, which comes out to 352.56. This means the vertex of our first rocket is 4.69 and 352.56. In the actual terms of this problem, remember the x is actually our time, and the y is really the height. Next, we're going to have to use our graph to find the vertex of the second rocket. We can go ahead and look at our maximum point, and we're going to have to estimate. We are definitely at 6 for the x-coordinate, or for the time. And then for the y, or the height, we look to be maybe about 575. Next, we're going to compare the heights, because it asked which rocket flew higher. So our heights are the 352 and the 575. So we can definitely say that rocket number 2 flew higher than rocket number 1. Part B says which rocket stayed in the air longer. Well, we need to say which coordinate tells us the time. Looking at our graph, that we see time occurs on the x-axis. So that means x, or really in the case of this scenario, t, represents our time. Let's draw a little sketch of rocket number 1 to help us know what our vertex is telling us. Rocket number 1 has a negative for a, so it's also going to open down. And we know that the start time is going to be at 0. Then when we reach the vertex, we know that the time was 4.69, and then we had the height. But we don't really care about that right now. So our vertex is halfway between our start and our finish. Because of that, we're going to have to take the 6.98, and we're going to multiply it by 2 to tell us the ending time of our rocket's launch. This comes out to be 9.38 seconds. Then we can use our graph to find the time for rocket number 2. We're starting at 0. It looks like it touches the ground here again when t is 12. So it's going to be 12 seconds for our second rocket. We can compare those times, and rocket number 2 also stayed in the air longer. Lastly, what if we want to know the height of rocket 1 at 2 seconds? The 2 seconds tells us what our t value is. T is going to be equal to 2. And we can plug this back into the equation. So we have the height is equal to negative 16 times t, which is 2, all squared, plus 150 times t, which is 2, plus 1. After evaluating, we'll find that the height is 237 feet.